And thank you everybody for coming. When I was asked to give this talk, I thought, well, this will be a fun talk to put together. There's tons of people here in the front. I give a lot of talks, but this is an entirely new talk that you're going to hear because this isn't a topic I had thought about much. But I should say that, and those of you who've seen the play may already know this, but those of you who will see it will find out. Henrietta Leavitt was really an amazing individual that has had a huge impact on astronomy for now really almost 110-ish years. And so that's really the purpose of the talk today. And so she's somebody who really didn't get a lot of attention. In fact, I'd say when I went to graduate school 30 years ago now, we didn't talk about her. But now she's become, in the last 2 decades, somebody really recognized for what she did. And it's an amazing story. I should say that I know very little about her personally, and so I'm hoping, I haven't seen the play, I've seen the play tonight. I'm hoping to learn more about that today, or tonight, but I will be telling you about her astronomy work and why it was so important. And so I thought I would start with one of the images that by now I'm sure you all have seen from the James Webb Space Telescope. This was the very first image they released back in July, 2 months ago. This is just a very deep exposure with the new telescope, pointed basically at this region of the sky for about 11 hours. What you're seeing in this image is just actually hundreds, thousands probably, of galaxies. Pretty much everything you see there, even the tiniest little dot, is a collection of stars, gravitationally bound, and we call it galaxy, and I'll talk about that a little bit later. These are systems with 100 billion to 200 billion stars, typically about 1 trillion planets, and just it's a gorgeous image, of course. But one of the things when you look at an image like this is you're really seeing it, of course, in 2 dimensions. We all know that the universe has this additional dimension, which is the distance. And in an image, as an astronomer, that gets collapsed, right, to these 2 dimensions. And so how do we know how far away something is when we look at an image like this? And it turns out this is exceptionally difficult. To this present day, it seems like it'd be easy, but it's not. And in fact, it's extremely important because as an astrophysicist myself, what I'm really most interested in is understanding how these galaxies change in time, how much energy they're putting out, and things of that sort I can't really determine if I don't know how far away it is. And that's really the purpose of the talk today. And so when you look at an image like this, you see there's objects that some appear brighter than others, and your first guess might be, well, how do we determine the distance? And maybe you would assume that we would just do it by brightness and say that the brightest things in the image are probably the closest. But it turns out that's actually terrible. It doesn't work in astronomy very well. And it doesn't work because astronomical objects cover huge ranges in sizes and energy. I love this diagram here on the left. This just shows you diagrams of what some of the bigger stars would look like. These are not real images, these are artists' conceptions. But what they show you is the sizes of stars. And I don't know if you can even see, the tiny little dot right down at the bottom is the sun. So make sure you saw that. Yeah, that's the whole point of the diagram. In fact, I can barely see it from here, so you probably have a hard time seeing it. That is the size of the sun. What you see here is that there are stars much, much bigger than the sun. Now, for a star, typically the bigger a star is, the more energy it's going to output. That's because it has a larger surface area, and that's just more energy to come out. And so you see here there's a huge range from the sun to Antares, which is the bright star in the constellation of Scorpio. But you know the brightest star, that is what star appears the brightest from the Earth, is actually the sun, right? And the sun appears bright not because it's a big star, as you can tell here, but because it's a very close star. And so unfortunately, distance plays a huge role, and this is why determining the distance is so important. You see that, by the way, Antares there is about 100,000 times the brightness of the sun. That means it's producing 100,000 times, the energy of the sun. The reason it appears as just a faint star compared to the sun is simply because it's so much further away. Okay, so the basic concepts we need to understand for this talk are entirely here. So how bright an object appears on the sky depends on 2 things. The first is the amount of energy the object puts out, and this is the real intrinsic quantity that we want to know as an astronomer. And this is what we call luminosity. That's the term we use in astronomy. This is the real energy coming out of the star. And the second one is this difficult one, which is how far it is from us, the distance of the object to us. So this kind of makes sense. I actually put an equation, which I never put equations in talk, but this I felt was a simple enough one. The brightness of an object is basically equal to its luminosity, that is the energy it's putting out, divided by the distance to the second power. And I'll explain the distance to the second power in a minute. But this kind of makes sense if you think about it. If an object is putting out more and more energy, it's probably going to be brighter. And as it moves away from us, it's going to get dimmer. And that's why it's divided by the distance. The distance squared, this is as technical as this talk will get. The distance squared is because light from a star propagates out in a giant sphere. You can think of it as like a sphere going outward. And the surface area of a sphere goes by the distance squared, the radius squared. And so that's why it's distance squared. What this means, by the way, is that the starlight drops very rapidly as you move away from an object. So, anyhow, if you could measure the brightness of an object, and you know its distance, you can actually reverse the equation and get the thing we really want, which is the luminosity. That's how much energy is the star really producing. But that's the thing we want as astronomers, but it's the hard thing to get because of the distance. So why is it hard to find distance? Well, it turns out that there's really only one direct way to measure a distance in astronomy. Actually, maybe this is the more technical one, I don't know. We're going to go back to some geometry here and some trigonometry. And the only way we can measure a distance to a star is to use a trick called parallax. And this is to take advantage of the fact that the Earth revolves around the sun, and that stars appear to move on the sky over the course of the year because our orbit has changed a bit. Now, I'm going to make you do an experiment I do when I go to talk to like third graders, but I want you to try to do it. It's kind of dark, I don't know if it'll work. But it's to understand this effect, you can do it with yourself because you have two eyes. And so, in fact, you have two different viewpoints on something. You may have done this before. You take your finger, you don't have to do it if you want to, it's valuable. Take your finger, put it about, say, a foot in front of your face. Close one eye and see where your finger is projected relative to things on the screen, for instance. Then switch eyes, and you'll notice that the position of your finger has moved, right? You actually did it, because people are laughing. It's exceptionally effective. What has happened is your viewpoint has changed, and the position of your finger relative to this very much more distant background wherever you were looking, which is basically fixed. Now, we can do the same thing at Earth. We can look at a star on January 1st, and it's going to be projected one place. You can go back on July 1st, and it's going to be projected a different place. And that angle that you move is called parallax. And you can see it there. It's kind of that little curved part there. And then it's a simple geometry to get the distance. The distance is a dashed line there. Because we know the distance from the Earth to the sun. And you know an angle, and from trigonometry, if you remember, I don't know if we do trigonometry, but, or our basic triangles, basically from those two things, you can measure that movement of the star, that angle, and you know the distance from the sun to the Earth, which we know we can get the distance to an object. It's a spectacularly simple process, but it works. Now I should point something out. Now I'm going to make you do the experiment again since you all did it. Now take your finger and move it much further away and do the same thing. And what you'll notice, I'm doing it too, is that it doesn't move nearly as much. That's the problem. The problem is, as you move away, as the star gets farther and farther from us, that parallax gets smaller and smaller. And in fact, it gets so small that at some point you can't actually measure it anymore. Astronomers can't measure it. And so while this gives us a direct way of measuring distance, it only works over a very small region of the universe. And this is that region. So here's a diagram. This is a drawing of what our own Milky Way galaxy would look like. This is our home, and you see there's a little sun there. And that tiny little yellow circle going around it is the area for which parallax can be measured. So what this means, yes, is that that's the region where we can directly measure the distance to any astronomical objects. And that's a pretty small region. We don't even get to the middle of our, not even close to getting to the middle of our own Milky Way galaxy, let alone the very distant galaxies that I study and other people are interested in. And so this means to study distances of things beyond this little circle, one needs to actually come up with indirect methods. And this is where Henrietta Leavitt comes in to measure distance. So let's just talk briefly a little bit. Some of you may have heard some of this in the play. I haven't seen the play, so I don't actually know what they say. But Henrietta joined Harvard as one of these computers. That's how people were referred to back in the day, 1903. Those of you who've seen the movie Hidden Figures, which I imagine many of you saw, an amazing movie, had the whole story was about the computers behind the scenes, the women doing those calculations that got us to the moon. We had a similar thing in astronomy. Harvard had actually the biggest group of computers, in fact, which Henrietta was one of them. So these women who were educated and trained would do all these calculations and measurements behind the scenes, hand that data over to the astronomer, and the astronomer would write the paper and become famous. Pretty much what happened, sadly. And the women were often not even recognized. They were not put on the papers and other things of that sort. It was a very different world. Just as a side note, women were not allowed to be astronomers, that is, to stand on their own and write their own papers and get telescope time until the mid-1960s. So many of you were probably here in the 60s. It seems like that, it's a long time to us, but if you tell a young person that, you know, we're talking 60 years ago, women were not allowed to be astronomers. It's really quite remarkable. Anyhow, Henrietta was apparently quite happy to have this job, and she was very good at it, very diligent. She was given the task of measuring the properties of variable stars in the Large and Small Magellanic Cloud. So first of all, what are the Large and Small Magellanic Cloud? These are the Large and Small Magellanic Clouds. These are these beautiful little systems. These are actually tiny galaxies that are the companions of the Milky Way. They're in the process of falling into the Milky Way as we speak, and they eventually will be absorbed by the Milky Way. And you see the large and small one there. This is an image from Carnegie site in Chile, Las Campanas. You can see these with your naked eye. They're really quite bright. Unfortunately, they're so far in the southern sky that you can never see them from here. Now, I should point out that the thing in the middle there is a telescope. That's probably obvious. But that telescope is called the Swope telescope. And the reason I point this out is because this was named after one of our computers at Carnegie. We had them here in Pasadena. Her name was also Henrietta, but it was Henrietta Swope. And the telescope's named after her because when we built our observatory in the late 60s, she wrote the check for the telescope. She ended up making, so she was, okay, I guess being a computer. And she made some really huge discoveries herself. So we have a telescope named after one of our computers there in the Swope telescope. Anyhow, back to the other Henrietta. These two clouds are these small collections of we now know they're galaxies. At the time, nobody knew what they were. Henrietta was given the responsibility of studying variable stars in these two systems. So what's a variable star? Well, a variable star, as you might guess, is something that varies. And in fact, this is a great little movie of this. What you're seeing here is a series of exposures in the Small Magellanic Cloud, the system that Henrietta was studying. And you'll notice that first of all, there's a lot of stars here. The reason why the background is so flooded is because this is a dense system with a lot of stars. But you'll see that the vast majority of the stars don't change. But you see these other ones that are popping in and out. These are stars that are varying in brightness over just a few days. This is a series that would maybe take place over a month, for instance. And so you see there's a good number of these variable stars. Particularly, these stars are called Sepion Variables. They're a very special type of variable, and that's what Henrietta was studying. Now you can imagine, this is a side note, if you look at this image, there's a lot of stars in this image. And so one of the things these computers had to do was measure the brightness of these stars with all these background stars. And it's a really complicated thing, and really took a lot of special care. You may be wondering, why do these stars vary? They vary because they physically are changing size. And as I mentioned before, as a star gets bigger, it has a more surface area and it tends to be brighter. These stars are brightest when they're the biggest, and then they actually are literally pulsating. And this pulsation is because they're at the end, they're near the end of their life, and in fact, in most cases, these are going to die in very large explosions we call supernovas. And so this is kind of an unstable period in the lives of these stars, but it makes them really valuable, and we can watch them vary in real time. This is some of the actual data that Henrietta used. What you see here is data. This is the Small Magellanic Cloud, the smaller of those two objects. And once again, you see all these markings here are markings that she made to identify the stars that she had noticed were varying. So now what this is, just to explain this a little better, this is a glass plate. This is how data was taken until the mid-1980s. You take a piece of glass, you put a photographic film on it, you would insert this into the beam of the telescope. So people think we look through the telescope. We don't really look through the telescopes. We take images on things. Now we do it digitally, but back until the mid-1980s, this was done on these glass photographic plates. So an astronomer at Harvard would have taken this data and would have handed it over to Henrietta and said, here you go, analyze the data. So the dark things in the image are in fact the bright sources, so it's a negative here. But you can even see from this image just how complicated this is. This is a very small system, very, very dense, a lot of stars. She was given the task of measuring these. So she would have been given a stack of these photographic plates taken on multiple days over months, maybe years, with the task of measuring for each one of these variable stars their brightness at any particular time. That's a tough thing. These Sepion variables, it turns out, vary in a very consistent way. And so this is an example, here what we call a light curve, this blue part here. This is kind of, if you take data, which you would have done, over many, many periods, each of the red points kind of represents a data measurement that someone like Henrietta would make. And you just plot it as a function of days, you see it on the bottom. And you can see these stars, these special variables that she was studying, have a very regular period. And in fact, we refer to the period as a very special term here. That is the term between the two minimums or the two maximums. In the case of these settings, it's similar usually. But you can see these things have a very, very regular period. Now this is where it started getting fun for Henrietta. Because she had data on over 2,000 of these variable stars between the large and small Magellanic Cloud. Data, as I said, over weeks or months that she had measured. And she noticed something right away. She noticed a very strong trend among these variables in these systems. What she noticed is that the stars that got the brightest took the longest in their period. In other words, it took them a while. They would do these very long periods. It might be days or even weeks between their brightest part and their lowest part, where the fainter versions would go much faster. So this is pretty interesting. But what did it mean? Because as I mentioned at the beginning of the talk, this is why I talked about this, of course, is that stars can be brighter because they're nearer or because they actually are intrinsically emitting more energy. And so how do you distinguish between these two possibilities? This gets back to the same problem. You can't measure the distance. These objects, by the way, the largest small Magellanic Cloud are about 50,000 light years away. They're well beyond the Milky Way, and so you can't use that parallax method. So how do you know what these things are? Well, she was pretty smart. She looked at these things and said, well, I look at these systems, it looks like they are probably collections of stars, and they're probably together in space. So what she did, she made a key assumption, that all the stars in the small Magellanic Cloud that she was measuring were at about the same distance from Earth, and all the stars in the large Magellanic Cloud were about the same distance as each other and from Earth. And if that's the case, distance kind of drops out. And what this means, if this is true, is that the stars that were brighter were actually more luminous. That is, they were actually putting out more energy because distance was taken out of the equation. Does that make sense? It's a little complicated, so that's why I'm just pausing there for a second. Basically, but the assumption here is the very key assumption that all the objects are at the same distance. Now, she ended up being right, and the reason she was right, let me give you an analogy. I was going to do this and I didn't think about how to do it. I'll give you an analogy. Let me make one up on the same spot. Okay. So it is true, if you think about these large and small Magellanic Clouds, they certainly are not all the same exact distance, right? Because otherwise they'd be in the same spot. But the variation within the clouds is going to be very, very small. And so, especially since it's very, very far away, those variations are small compared to the distance we're measuring. So in some sense, this approximation is fine, is the example I did. If I tell you what is the distance to New York City, and you make measurements in Queens and Brooklyn and Manhattan, and give you those measurements, honestly, if you average them out, they're going to be good enough. Those variations between those various places, right, are going to be very small compared to the very large distance between the Earth. So hopefully that helps a little bit. That's basically what she's assuming here. She's assuming in these objects, there's such little variation, we can say they're effectively the same distance. And you get the answer pretty right. And you do get the answer right. So with this assumption that the distance, that all the objects in the small Magellanic Cloud are together, all the ones in the large are together, then this means these variations can tell you the luminosity directly. And this is really interesting. And from it, she's able to derive a law. You can go backwards and go across to the distance. So this is the law she derived, we now call Leavitt's law. It was not called Leavitt's law for a long time. So basically what she did was, as I said, the longer the period, the brighter and the more luminous, in this case, because distance doesn't matter, an object is. And there's a very tight correlation, this is real data here, between these two. So as you go out on the x-axis, you're seeing period, that is the variability by days. That is the peak, once again, or if you take the lowest point and the next lowest point. And on as you go up on the y, you're getting to more luminous objects, more energy. See, the relationship is great. And so, in fact, if you can measure the period, and you tell me it's 10 days, I can go up and tell you exactly how much energy that star is putting out. This makes these objects what we call standard candles, which means we can find these Sepion variables all over the universe and get approximate distance measurements to those objects. Okay, well, I basically just said what's there. This is basically a method by measuring the variation of these stars, you can get the distance to an object. Now, that may seem kind of, well, it seems kind of simple. The reality is it's much easier to measure these periods and these variations than it is to get the details, other details of stars much better. And so, from an image like this, one could measure the distance, for instance, of the smaller object. Okay, so Henrietta Leavitt does this, publishes this. People start reading it, but no one makes a huge deal of it. But at the same time, there's a revolution going on right here in our backyard, here in Southern California. Starting with Andrew Carnegie and George Hale, names you're probably familiar with both of them actually in this area. Of course, Andrew Carnegie at the turn of the century was the wealthiest man at times in the world, and decided to give away his vast fortune for good. George Hale on the right there was a solar astronomer at the University of Chicago. He had just built a telescope in Wisconsin and decided that Wisconsin, because of its weather, was not a great place to do astronomy. And he was convinced Southern California was the place to do astronomy. And so he read in the paper Carnegie was giving away his vast fortune, and he convinced Carnegie to build an observatory here in Southern California. And thus the thing that is now called the Carnegie Observatories was born. For many years it was called the Mount Wilson Observatories, but we changed the name because we now have multiple facilities. Anyhow, George Hale, as the first director of the Carnegie Observatories, was exceptionally ambitious. He was very, very good at getting money from people. In addition to Andrew Carnegie, he got many other wealthy business folks here in Southern California to help fund telescopes with Mount Wilson. George Hale built the three biggest telescopes in the world back to back. These first two right up here on the hill of Mount Wilson, and then eventually the Palomar 200-inch. He unfortunately died and didn't live to see that one being built. And Palomar's down here to make you one for those of you who may be not familiar with it. Okay, so let's see, what do we do with these telescopes? Well, as I said, the 60-inch was the first one to come online. It came online in 1908. As I said, it was the biggest telescope in the world. And the timing for this was great because there was a very big debate in astronomy going on about the nature of our own Milky Way galaxy. Now, if you go out to a dark side, and you see this is, of course, what we refer to the Milky Way when we go out on the dark side and see it. You can see it here in LA, but astronomers had noticed that the Milky Way pretty much wraps around the sky. That is, any time of the year you can see this band kind of going overhead. It goes effectively all the way around us. And so astronomers had naturally assumed, because it goes all the way around us, that we must be in the middle of it. That is, that the sun must be at the middle of the Milky Way galaxy. Humans have a tendency to always assume we're the center of things. This is a general problem. You will remember, of course, about 400 years earlier than this, Galileo, Copernicus, and then Galileo did the observations that showed that the sun was actually the center of the solar system, right? Prior to that, the Earth was the center of everything. Then we moved the center over just a little bit to the sun. And basically, up to 1918, we still thought we were the center of the galaxy, which at the time was the whole universe. So really, up until 1918, humans thought we were the center of everything. So there was a guy who really wanted to understand this, and his name was Harlow Shapley, working here at the Carnegie Observatories. And Harlow was very interested not only in the location of the sun, which, as I said, most people assumed was in the middle, but he was curious about the size and scale of the Milky Way. And he noticed there were these very interesting systems called globular clusters. There's a beautiful example here. These are these very, very dense star clusters that contain up to 1 million or sometimes a couple million stars in them. And he noticed that there were a lot of them. There's about 200 in the Milky Way. And he said, well, we can use these to kind of map out the size of the Milky Way by just determining how the globular clusters are distributed. And what you'd expect if the sun was at the center of the galaxy is that the globular clusters would be evenly distributed kind of around the galaxy. And that, of course, is not what he found. What he found, in fact, is that the top there shows you what one expects if the sun was at the center. These clusters would kind of be around the whole galaxy. Instead, what he found is almost all the globular clusters are on one side of the, basically distributed on one side of us. And this tells you that we are kind of at the edge of the Milky Way galaxy on one side. Now, how did he do this? He did this by using Henrietta Leavitt's law. he looked for these Sepion Variable stars in the globular to measure the distances. And so if he didn't have access to that law, he would have had no idea how to distribute them. You could just, once again, you could distribute them how they appear on the sky, but the key here is the distance. You need to know that they really all are on one side of you and far away. And so this result, 1918, humans finally understood with Harlow Shapley that the universe, that the Milky Way, that we are not at the center of the Milky Way or the universe, thanks to Henrietta Leavitt. The next big Bell Wilson telescope came in 1917. That's the 100-inch telescope. And this is, I argue, the most important telescope ever built because of the work of the next gentleman I'm going to talk about, a very famous astronomer named Edwin Hubble. You, of course, will know him from the Hubble Space Telescope. He also was a Carnegie astronomer. He arrived here in 1919 in Pasadena. And he made the two biggest discoveries of the last 400 years. Once Harlow Shapley had shown that the Milky Way, he made this measurement of the Milky Way, he found that the Milky Way was much larger than people realized. And even though we are at the edge of it, he was convinced that the Milky Way had to be the whole universe, because the Milky Way was so big, there couldn't possibly be anything beyond it. But there were these fuzzy objects on the sky that looked kind of spiral-like, that some people thought could be things like the Milky Way just further away. But how do you figure out what they are? Well, Edwin Hubble figured out what they were, once again taking advantage of Leavitt's law. So Hubble was interested in studying a completely different class of stars in these, what were called spiral nebula. This is an example of one of them. This is the Andromeda Nebula, which is now the Andromeda Galaxy. And you'll see some ends on here. Hubble was studying these stars called novas. Novas are stars that get very, very bright. They have like an explosive event, and then fade for about 100 years. And so Hubble was, like Henrietta, was taking data over multiple days, multiple nights. And what he noticed, you see these things labeled as N. You'll see at the very top corner there's one crossed out N with a VAR and an exclamation point. What Hubble noticed when looking at data the night after this was that this particular star did get brighter, but it had gotten fainter, and then it got brighter again, which is not like the novas. The novas, as I said, take 100 years to do that. He knew what he had instead was a Sepion Variable star. The exclamation point is key here, because what this means is he knew from Henrietta Leavitt's work that he could measure the distance of this fuzzy thing. And when he did, he showed that this thing was in fact 2 million light years away, well beyond the Milky Way. He effectively discovered that this was another galaxy like the Milky Way. He went on and, of course, did many more. And what he showed is, in fact, the universe is filled with galaxies. The Milky Way is one of, now we think, close to 10 trillion galaxies in the universe. This is effectively the discovery of the universe. It happened right here, right in Pasadena, right next door, using the telescopes of Mount Wilson. But it only was possible because he had access to distance to this thing and other things from the Henrietta Leavitt law. That's why she was so important. It's a wow. 100 years later, it's good. But you can go one step further. Hubble started then looking at these Sepion variables in other galaxies. And he noticed another interesting trend, that if you looked at the galaxies that were farthest away based on their Sepion variables, they appeared to be moving away from the Milky Way at faster rates than the nearby ones. So this is a different correlation than Henrietta's, but it looks very similar, so that's what I'm going to here. As you go out in distance, things farther away from us are never going to speed away from us. This is called Hubble's law, because this is what we found. And what this is a really interesting result, which basically was the first proof that the universe was expanding. Now, I have to be careful, because Edwin Hubble did not ever say that, because he didn't like the idea of an expanding universe. It made him very uncomfortable. It makes all of us very uncomfortable. But what is happening is, you imagine, an analogy here is you have a raisin bread, which is, you cook the raisin bread and it's raw, and you put it in the thing. As it heats up, it's going to, imagine with all the raisins. As it expands, the region between the raisins, the bread is going to expand, right? So the raisins are actually going to be moving further and further away from each other. It's kind of how you think of the universe. It's not a great analogy. It's not as good as you can. But what this means is that basically the objects that are further away from us, there's just more space in between us to grow as the universe expands. So they appear to be going even faster and faster away from us. Truly remarkable result. And of course, if you think of an expanding universe and trace it back, the universe had a beginning, and that was, of course, the start of the Big Bang. The theory, not the show. Okay, so I want to show this. This was a huge thing here in Pasadena in the 1920s and 30s. Edwin Hubble was a celebrity. He was on the cover of Time magazine for this. This is a picture from our beautiful Hale library. If you haven't come to the Carnegie Observatories, you must visit. our historic site. And there's, of course, Albert Einstein. This was a day where Albert Einstein admitted his biggest blunder. Albert Einstein had assumed that the universe was static, that is, that the universe did not change in shape. And even though Edwin Hubble's result came in 1929, it wasn't until he could come to Carnegie and spend time with Edwin Hubble, who's the second from the left there, that Einstein was convinced that the universe was in fact expanding and that he had made a mistake in his equations. So that happened in 1931. It's beautiful. It's right here in Pasadena. Okay, almost done here. This is Hubble's original diagram. This is the new Hubble law with more recent data. It's plotted in a slightly different way, which is why the curvature looks a little different. Don't worry about that. This is just the way it's plotted. Edwin Hubble's piece here is literally the first dot on that. And so we now can measure distances and the velocities of galaxies way out into the universe. And you see it's a very nice relationship there. But I want to point out something. The Sepion limit, to measure this, you have to measure the distance of these galaxies. The Sepion law, Leavitt's law, only allows us to go out a certain distance because at some point you just can't see the stars anymore. The variable stars are just too faint as the galaxies are too far away. So how do we do the rest of the measurements? Well, astronomers got very clever about 25 years ago and discovered that there's another star you can use, which is an exploding star called a supernova, type 1a. And this particular supernova always has the same exact luminosity for reasons we don't fully understand. But it always seems to have exactly the same luminosity. And so if you know the luminosity of an object and you can measure its brightness, you can once again determine the distance. So what is happening in this case is astronomers looked at nearby galaxies where they had a distance from the Cepheids, and they had the supernova, and they could use the Leavitt's law to find the distance, and then apply that to the supernova, and then the more distant objects, they just use the supernova. So we basically, this whole thing, even though the Cepheids only go out a certain distance, is really based on the Cepheid distances that Leavitt found. So if you look at this very closely, you find something super interesting. And that's that the Hubble law, if the universe kind of expanded at the same rate over time, it would follow a line. You can see it there on the right, there's the theory of it. You see that red line there on the left. That's where the universe should be going if it was going at the same speed all the time. But what we found, and once again from these distance measurements, you can see the data on there on the left actually goes well above that line. And this means that the universe was slower in the past. The acceleration of the universe is accelerating. It's actually expanding faster now than it did in the past. It's a huge result from the late 90s, early 2000s. And what this meant was that why is the universe expanding? There's really no explanation for what the people had. It meant there must be an additional force we don't understand, which is now known as the dark energy. We don't really understand it, but this is a force that's actually leading to an expansion and an acceleration of the universe. So the universe is going faster today than it was in the past. But this, once again, would not have been possible without Leavitt's law and getting those measurements. Okay, I wanted to just at the end here return to this beautiful image. I could talk about this image right now, I'm not going to. If you have questions about it, I'm happy to answer them. But the reason I like this image is because this very first image with the James Webb Space Telescope allowed us to see the most distant objects we've ever seen. And the thing I want to point here is I want to remind you that this is once again a kind of a rickety ladder. It started with parallax, so how do we measure the distance to the most distant things? We started with this parallax, and then had this Cepheid method that Henrietta Leavitt came up with, then these supernovas, and now that we've got other similar methods to expanding. But they all kind of go back and rely on each other. And so in some sense, Henrietta Leavitt's work is allowing us to measure the distances to the most distant objects in the universe. And what is the most distant object in the universe? In this image so far, this one is 13.5 billion light years away. So what that means is the light we're seeing left that object 13.5 billion years ago. Now to remind you, the universe, the universe is 13.8, Big Bang is 13.8 billion years ago. So this is an object being seen just hundreds of millions of years. It sounds like a lot to a human, but to astronomers it's very short, after the Big Bang. We're seeing almost the very first stars and galaxies. And James Webb is almost certainly going to see those first stars and galaxies in the coming months. But once again, the distance matters. That's why it's so important. Okay, so with that in mind, I have this great picture of the Harvard Computers at work. I thought this was a great picture to end with. Because I just think what the story of Henrietta Leavitt reminds us is that there's a lot of people that it takes to make work happen in astronomers. And the astronomers, including myself, we get a lot of credit, we get to write these papers. But in a case like my own, I use telescopes that were designed by engineers, right? I use We have office staff, business staff, people behind the scenes, young postdocs and graduate students that work with us that often are doing the work that's similar to what the computers would have done in the past. It really takes a lot of people to learn about the universe. We're making great progress, and it's very nice to see that the computers are finally getting their credit after all these years. And finally, I just point out that if you didn't know much about Carnegie, you know a little bit about us today, but we do a whole bunch of stuff. This is a beautiful picture from our site in Chile. And if you want to know more, we have all sorts of public talks and things. And there's going to be another speaker in October 2nd, I think. Is that right? Our librarian is going to talk more about the computers here, so I hope you come back for that. Feel free to follow us on the various social media platforms, or send me an email, and I'll be happy to answer questions at this point. Thank you. Great question. So there was a lot of interest in the Southern Hemisphere, primarily because of these Magellan clouds, because everybody recognized they're kind of unique opportunities. We don't really have the equivalent of that in the Northern Hemisphere. And so Harvard actually built their first observatory in Chile in the 1800s. And in fact, when George Henry Hale was debating to come here to build Mount Wilson, Carnegie considered building an observatory in Chile back at the turn of the century, deciding Mount Wilson was easier because of travel. In this particular case, however, the Henrietta data was actually taken at an observatory in Peru. For some reason I don't quite understand. Harvard had an observatory in Peru. Peru is not nearly as good as Chile. It's not as dry as Chile in the conditions. But that data was taken in Chile, so presumably the astronomer, they sent an astronomer down who was taking the data, probably lived in Chile or in Peru for months at a time, and then brought that data back. I should point out that these glass plates, there are two places in the world with the most glass plates, and that's Harvard and Carnegie. And in fact, we have about 250,000 of these glass plates in our basement here in Pasadena. Well, many of the Northern Hemisphere ones, but the particular data set she had, this was interesting to me too. You can't see this from those locations, and so this was a separate telescope. So in fact, there may have even been others. I don't actually know that Harvard seen so much, but for instance, here we have data from pretty much every telescope in Mount Wilson, beyond the two I mentioned. But this data was definitely taken in Peru. The data that she used, because it was these particular small amount of.
So that was probably later, because in the beginning they were using the great refractor when she first started.
I should clarify, and I haven't seen the play. This was her second time at Harvard, was when this work was done. So she came in 1903. She had been at Harvard prior to that, which is probably what they covered in the play.
Right.
Yes.
Yeah, they do her beginning when she was when they're, because the women weren't allowed to touch the telescopes. They couldn't look at the telescopes.
That was still true to the 60s, actually.
Wow.
Yes.
But anyway, thank you. That's what I wanted to know.
Yes. So now I'm looking forward to it because, as I said, I know very little about her as a person, and so that's why I'm looking forward to the play myself.
Harvard is digitizing its, 400,000 glass plates. And in the course of doing that, in order to get a good picture, they're scrubbing the notes that were written on the back by the author. Now, they are digitizing those, and the curator of the collection has managed to save several hundred with the original scribblings on it. So I'm interested to know whether you are digitizing and what your attitude would be to the scribbles on the back.
So this is a great question. Every time I take somebody to see our collection, they ask, that's the first thing people want to ask me, because we have all these valuable plates. And as I argued, probably the most important, really, because it really has all that Chapman and Hubble stuff. And another very famous Carnegie Astronomy, Vera Rubin, all of those plates we have. And so my own take, we are not digitizing all of them. What we've done instead of actually doing it that way is we bought a camera, because now the cameras are great. We have a camera set up that allows us to take a very high resolution imaging, which allows us to keep the writing on it. And so we've done that for all the famous valuable plates. And we have a process we've been going through and trying to do as many as we can. But 250,000 plates is a lot. Now, the other reason, well, certainly some of the plates, like Hubble's variable plate, I mean, that one's hidden and buried. It comes out very rarely. I've seen it twice in my 30 years at Carnegie. Those we keep, we take special care of. But the vast majority of the plates actually have very little scientific value at all. And that's because most of the things we can do, we could redo these observations in a fraction of the time and much better with our current telescopes and digitally. And so for the vast majority of them, they don't really have a lot of scientific content. There are some exceptions. One of the exceptions would be if you wanted to say a star explodes in a particular region of the sky, and we did have an image of that region of the sky. It's possible somewhere in our 100-year history we haven't, so that happens. Where people will call us up and say, do you happen to have an image of this region of the sky? And then being able to pull it out and go, oh, here's the star that exploded is super interesting. So we do that. The second one, which is actually more interesting to me, is we have images of comets. Particularly, we have Hale's comet from 1910. So in 1910, the Earth basically went through the tail because this comet is spectacular. And the biggest telescope in the world was the 60-inch over Melbourne. So we have this huge series where we observed it many times per night back in 1910. And that you could never reproduce, right, because that won't happen in our lifetime. So I think for the most part, though, the plates aren't terribly valuable, aren't worth the process of digitizing them. But I am absolutely against getting rid of the astronomer's work. I find that some of the most fascinating things is the work. I love that image with all her markings because it automatically shows you just how detailed that work was. So I think that's a huge mistake they're doing, but I'm not in charge of Arkansas. I was a graduate student 30 years ago. There was a thought that the universe would expand, but that the universe expansion should be slowing down. The reason it slows down is because there's objects in the universe called galaxies, and they have gravity. And so we know gravity tries to pull things in. And so the idea was that the gravity from objects should be slowing down the expansion. And at some point you might hit a point where you stop and then you recollapse back, and it's called the Big Crunch. And so, there's also people who think that that has happened many, many times. Then the dark energy was found, and the acceleration is so strong, and it seems to be increasing, that in fact, most people think the universe is likely to kind of get what's called the Big Shred, which is, in fact, go to the point where it just keeps accelerating faster and faster, and at some point, it gets so strong that it overtakes gravity even locally. So let me back up and say, the universe is expanding and accelerating. Why are we not being torn apart? And the reason is gravity is dominant on small scales. This energy, dark energy, is dominant on big scales. But if dark energy continues to get more and more powerful, at some point it'll overtake gravity. And basically stars and planets and all of us will be shredded. And basically they'll probably use nothing, not even atoms at that point. And so that's why it's called the Big Shred. So that's kind of what most people think is likely to happen. However, I'm going to put it, as I said, 30 years ago, I said an entirely different answer. So I'm very nervous. We don't understand what the dark energy is or how it operates. Because it's entirely possible the dark energy accelerates and then reverses direction and we go back to the Big Crunch. So I think we don't know enough, but the formal answer of astronomy will give you, oh, the universe is going to expand forever and eventually you'll have this Big Shred. Like I said, I wouldn't bet your house on it. I think the answer to the other things we won't know, probably because unless we have a much better understanding of dark energy in the near term, this is hundreds of billions of years from now. So this is not something to keep you up at night. There are things in astronomy to be more worried about. It's a peaceful universe.
The object you showed at the end of the presentation, the one that's 13 and a half million years away, what was it? Is it a galaxy?
It's a galaxy. You have to take at that point, basically what we're seeing are galaxies. You can't really make much of the image because there's very few, this is an exceptionally faint thing, and so they've smoothed it to make it look like it, but it's a galaxy.
What's the magnitude?
Oh, actually, don't know. It must be, well beyond that, because even Hubble would see, Hubble doesn't see this object, so it's much fainter than that. It's probably 35 or something like that. I really had no so. I should say that there's, I really don't know. What I would say, and it's certainly well outside of expertise, the thought is that it's an additional force of some sort. I mean, it's basically an anti-gravity force of some sort that the universe. But what's interesting about it is that we do see it's building up very, very rapidly over the last, I'm just going to say recent years, but not recent, 5, 10 billion years. It's increasing very, very strongly at such a huge rate. I believe the observations really are consistent with the accelerating universe, but at the moment nobody has a model for the dark energy that I would find convincing. That is way beyond, that's going to be a physicist's problem probably, well beyond the astronomer.